hasn't shared it. Let's go ahead and introduce the next presentation. Now, we're entering some of the sciences. There has been one change. It will be the third paper, which was going to be an introduction to the biology of the cave. Matt, is it Niemiller or Niemiller? Niemiller. Matt was going to give the presentation, and he has thrown out his back, and he is unable to drive up, and so that one will not be given, but that is the one right before lunch, so it's okay. We'll just take a longer lunch. Hal Love will also be showing a short piece of film after the two geology presentations. Now, I had not met Christian DeCelle. This is his presentation, but as some of you know, I don't know where he's from originally. He went to Western. I think he might have been one of Dr. Cambisis's students, and studied geology and so on. He was one of the fairly early Helm's Deep cavers. And when I got involved in the project, I would ask people, well, you know, like what rock unit do you think it is? And they would say, well, you know, Christian thinks it might be this. And I would say, well, what about the structure? And they'd say, well, you know, Christian has done some work on that. And what about the minerals? Well, oh yeah, Christian had a couple of those identified. And what about the stream? Oh yeah, he's done some measurements down there. So I thought, even though he cannot be here, his current job, I guess he's a karst hydrologist with the U.S. Forest Service. He is posted in Alaska. Unlike most of us, he cannot get here in one day. It takes him a day to get to the airport, and then all the transfers. So he just couldn't afford to take 5 days to come here because he started an expedition in Alaska on Monday, which he's leading, so he can't miss it. So I asked Christian, he told me 3 weeks ago he didn't think he'd be able to come, but he still wanted to contribute. He's been working on a report for Jonathan, the owner, and for the project, pulling together some of his initial ideas. Basic stuff, which for most caves we know, but not this cave. Like, what rock unit is it in? Where does the water come from? Where does the water go? If I light the rock with my lighter, will it catch on fire? And Christian has some tentative answers. So I'm going to present some of his material. I am not a geologist, but I would have gotten Hal or Jim to do it, but I didn't get the report till last night. So I had to read the 50 pages and convert it to a PowerPoint. Wow. Here we go. He wants to kill, so that's down here. Just go down here and hit. Oh, hide. You don't want to hide it. You want to kill it.
We want to stop sharing. Okay.
Okay, thank you.
There we go. Yeah, I'm sorry. Yeah, no, I have to sit here.
So the cave is generally, the cave is generally separated into two main sections, as we've already heard. Well, first I should do the title, Helm's Deep Cave, a draft of early thoughts on morphology, geology, hydrology, and speleogenesis. Christian has done this, but there's an echo in here.
Okay.
But this is not, I mean, he's been bouncing ideas, and so he wanted to make sure that he credited Clint Elmore, Michael Ketzner, Jim Smith, Sid Jones, Hal Love, Maggie Brodsky, Riley Blackwell, and Pat Cambises. Okay, so the cave is generally separated into two main sections, the river and the maze. The river is known to flow northward for about 4,000 feet, much of which is a large passage. The maze is much more extensive. Bob, what's going on? It's the audio from that. The audio from that. Okay. Now, the maze is much more extensive than the stream. It winds through sections of dry walking borehole and muddy crawls, There are only two places where the river and the maze intersect. Both are at large breakout domes near the entrance of the cave. Hydrologically, the cave has no known inputs, but it does have they have some guesses, possible guesses, on the outputs. The water is almost exclusively seen in the river and the cave, and at the far northern extent of the cave. The passages of the maze are characterized into three morphological patterns. There's the upper shale, there's the middle maze, we call it the maze, and the lower maze, which we call Mirkwood. The passages are all found within a 25-foot thick section of the stratigraphy. The upper shale is found at and above the contact with the limestone and the shale above. The middle maze is found in about 10 feet of limestone below the contact, and then the lower maze, or Mirkwood, is found in about 5 feet of limestone just below the maze. The dominant morphology seen in an area may be controlled by the absolute elevation of the limestone. Anyway, these are continuous and they're grouped together. And so you can see here the cave has been divided into these morphological sections. The middle maze is generally considered the main level of the cave. The large concentration of continuous shale passages are especially found in the southern and western portions of the cave. When the shale is broken, it gives off a sulfurous hydrocarbon smell. In one case, Christian DeCelle attempted to light the freshly broken shale and was able to get the flame from a lighter to stay lit on the rock for about a second. He attempted this on many other rocks and found that it is difficult to get a rock to stay lit. Currently, the shale passages are thought to form from overdevelopment in the maze. This is supported by the lack of maze passages where the shale passages exist, as well as the obvious breakdown collapse at every transition between the two types of passages. Similarly, the shale and limestone maze passages seem to occupy the same footprint and are nearly indistinguishable on a line plot, but there does seem some evidence that does not support the maze collapse theory in the larger western shale boreholes. The massive western boreholes may deserve distinction from the typical shale passages. These passages are much larger and have a much more of a square-shaped cross-section, and the western boreholes are also a few feet higher stratigraphically. And of course, this is just an example of a piece of shale here, but of course, I would say the Native Americans put that there, but it is certainly shale. The middle maze passages are formed with the ceiling just a few feet below the Maury Shale. They're thought to be the primary level of development in the cave. These passages are generally between 5 to 7 feet tall and 10 to 20 feet wide, with a flat clay floor, as we've heard from Jim, of unknown thickness, at least a few feet, and the walls of these passages are rounded and the ceiling is flat. There is a transitional level that exists below this, but it hasn't been looked at much. Mirkwood is the name that the explorers gave to the lower level crawling passages throughout the cave. As we've heard, the cavers often joke that, quote, all roads lead to Mirkwood. And if there is a passage that looks like it's going downward, it will quickly lead to Mirkwood. It's almost like a state of mind, as well. At every extent of the cave, north, south, east, or west, there is Mirkwood. The crawlways of Mirkwood are generally 10 to 20 feet high. They average about 3.5 feet high. The passages here are more convoluted than in the middle maze. And it is worth noting that while the level descriptions can be used to generalize about any passage in the maze, these descriptions become less accurate as you move north into the cave. The passages in the north are probably somewhat different. They're lower, they're closer to the water table. The dominant hydrological feature of Helm's Deep is the river, which typically flows through passage 20 to 30 feet wide and 25 feet high, punctuated by the large breakout domes. The river flows approximately 3,200 feet north-northwest. It originates from a sump in a large collapsed room and ends in another sump. And we've already heard from Jason about the penetration of that. The river is known for being stable and clear. 2 discharge measurements were made by Sid Jones in the fall of 2022, measuring 13.7 and 15.1 CFS. That's taken during low water. On February 12, 2023, the river was measured by Christian DeCelle and Sid Jones at approximately 20 CFS. Only once, on January 21st, 2020, has the river been observed in a murky, swollen state, and Jonathan talked about how they estimated maybe 30 CFS at that time. And then, of course, this shows during ordinary water, this is what the passage looks like, and then, of course, in high water, and so this is the same features, and this shows the water line from the other one transposed onto this one. It's unclear what role, if any, the river played in the formation of the maze. Along its map course, the river is generally 80 to 90 feet below the maze. The maze and the river only intersect at 2 points, the entrance and then over at BBA1, which is not far away, large collapsed domes. And these are, I think, happenstance connections. That's Michael talking, not me. I don't know anything. The river is likely intersects the maze at the northernmost point in the cave. There is a large deep pool there called the Pale, which is shown here, and so they suspect that is the same water. Now, does the downstream river sump represent a true vadose phreatic border of the river? Question mark. Is it flowing north along a similar elevation before intersecting the maze passages where they have dipped down to that elevation? Question mark. Does the river flow remain concentrated in a single phreatic passage, or does it reach a sort of water table that then becomes diffused? Is this diffused flow moving through an anastomotic branchward of passages similar to the maze? That is the water similarly now doing what it did to create the cave? That is, could the phreatic river flow represent a present-day formation of maze passage? That is, has the cave formation been continuous since its inception? Or perhaps could a slowly lowering phreatic zone explain the formation of the maze? Currently, there are no known discrete hydrological inputs into Helm's Deep. From its upstream to the downstream end, there are no tributaries entering the river. On the surface, there are currently no known insurgences that are suspected to flow into Helm's Deep. Likely insurgences should probably be looked for on Trace Creek and its tributaries to the south, as well as the headwaters of Rockhouse Creek and Cotton Branch. Water likely does not enter at a discrete point, and so it may show in the surface as a losing stream. The river's stable, ever-clear nature that does not respond to most rain events lends to it being fed primarily by diffuse inputs. These likely come from fractures in the overlying Fort Payne Formation. However, diffuse inputs do not then explain the extremely high murky water that Jonathan observed in January of 2020. There are no known resurgences currently known for Helm's Deep. It is suspected the water resurges somewhere to the west or the north, and this shows, of course, here's the cave, and this shows some of the springs and drainage down here, if it does indeed flow that direction. So there are possible springs in Hurricane Creek, Short Creek, Coon Creek, or the Buffalo River, but only 2 areas have been found that could represent a concentrated discharge of the spring. That would be the Hurricane Boiling Springs complex, and then the Rise Mill Spring, previously known as Sid's Big Spring. Apparently it already had a name, Sid, sorry. The Rise Mill discharges significantly more than the Helm's Deep River. It resurges, 500 feet from the Buffalo River, which is the main water stream in the area. No other large springs have been identified. At the moment, the Hurricane Creek Springs are the most likely candidates for the output for the Helm's Deep water. The Hurricane Springs are made of Hurricane Cave Spring, Lower Hurricane Spring, Boiling Spring, which Jason has actually tried to dive, and Boiling Accessory Spring, which I didn't even know there was an accessory spring. They're all found on the half-mile stretch of Hurricane Creek. Each spring's on the south side except for the Lower Hurricane. On February 12, 2023, they were observed to have a combined flow, which is very similar to Helm's Deep, of about 20 CFS. And of course, more detailed measurements from the river, especially a level logger recording stage alongside with a rain gauge on the surface, would provide invaluable information to the river's response and flooding. And I believe Dr. Cambyses, in fact, will be talking about her attempt to do just that. And then, of course, why do they think the spring. What I'm looking at here really is, and again, I'm no expert, but conductivity. So look at the conductivity in the cave, in the Helm's Deep River, a 108, and then look at it at lower hurricane, above boiling, and boiling. I mean, these are really pretty close conductivity readings. So that's, I think, what maybe why they suspect what they suspect. A dye trace has been planned for 2024. You know, there was the early attempt, but it was in flood conditions. The project has received, Christian, I guess, has received a grant from the Tennessee Cave Survey, and this is the planning document. If you're interested, we actually have Christian's PDF report. He's got a link to it. We're going to write that. The best way to do it would be not the link. It'll be the
QR code?
Yeah, the code.
Barcode,
Yeah, the barcode he sent. So in fact, we can do that during the next break or at lunch or something. So Helm's Deep Cave is 187 feet deep. It's formed in the Fort Payne Formation, Chattanooga Shale, if it exists, we can debate that, and then Silurian limestone. There are multiple unconformities between the bottom of the Fort Payne and the top of the Silurian limestone. Geologic maps in the area indicate that the Chattanooga Shale is along the Mississippi and Devonian boundary. Limestones are absent, and that the youngest limestone in the area is the Silurian, that is the Decatur limestone. So we're not sure that's all accurate. Regionally, the rocks dip to the northwest, although there are likely local structures which affect the dip of the rock in the cave itself, and he actually talks about that in a minute. Nearly the entire stratigraphy of the cave, so if you're a stratigrapher and you want to do work here, the entire stratigraphy can be seen in the entrance. And if you're interested, Christian describes all of these units and which ones he thinks that the cave mostly forms in, and his evidence for that, and so I will recommend the PDF. Now, it is a work in progress. All of these are works in progress. But it is a good starting place, that's for sure. Regional dip was investigated by Christian using the ArcGIS and high-resolution DEMs. The LiDAR hillshades showed that steep cliffs typically form at a certain elevation within the area. It was noted these cliffs roughly follow the contact between the Silurian limestones and the Fort Payne Formation. These cliffs likely represent the transition from the strong siltstones and shales at the bottom of the Fort Payne to the eroding limestones below. Identifying the base of these cliffs and their elevations across a wide area should give an estimate for the bottom of the Fort Payne, and thus a rough geologic contour would show this regional dip. So that's what he did. Over 100 points were identified. Their elevations were interpolated to create the surface shown here. The data does show a dip to the northwest, and that, of course, generally agrees with the local geologic map. A rough estimate puts the rock at dipping to the northwest at a rate of about 1 foot for every 650 feet. And so in the end, this analysis, confirmed what was already suspected or known. To understand the local dip in the cave, the elevation of the bottom of the Murray Shale was measured in relationship to the nearest survey point. Then once the elevations of the Murray Shale were known, they were plotted onto a map. They were labeled and then used to estimate contours. The data show a pronounced high point in the southwestern reaches of the cave, where the highest measured point was at the southern foot of Lonely Mountain. From this high point, the cave appears to dip away in all directions. To the west, east, and south, the cave seems to dip away slowly, while to the north, the cave appears to dip consistently at about 0.5 degrees to the northwest. Wherever the rocks dip, so does the cave. Even in the southern and central sections of the cave where the dip is not consistent, the maze passages follow the same beds. And so anyway, you can see this for yourself. The rocks in the northern half of the cave dip northwest or at an angle too steep to match up with the stratigraphy seen on the surface. So some structure, a syncline, unlikely but possibly a monocline, or maybe a large fault, They must exist north of the cave to make up for the difference. No faults approaching that size have been observed on the surface or in the geologic maps, and there's no evidence on the LiDAR of any abrupt shifts in lithology. As such, a syncline between the northern edge of the cave and Coon Creek is considered likely. Now, if this northern syncline model holds true, then the recharge area for the cave has to be revisited. Currently, it's thought that the water in the river is recharged diffusely from the south and east before concentrating, then flowing north, and then hitting the water table. But with this new model, a northern component must be considered that would provide for a recharge north of the syncline. Strong joint sets and faults are present throughout Helm's Deep Cave. These act as a point of weakness, causing passage terminating collapse. This is especially noticeable in the western borehole, although it's also common along the southwest border of the cave at the edge of, Mirkwood. Several faults with vertical displacement have been noted, such as the fault shown here. Reports of strike slip faults are also common, related to distinct feathering along certain fractures or in large shear zones. It is not uncommon to find large breakdown piles in the western borehole truncated by multi-foot thick sections of semi-lithified crushed fork pane siltstone. Fractures in the cave predominantly trend northeast, about 220 degrees. They are ubiquitous, but their influence is not always apparent. The anastomosis of the primary maze are generally angled parallel to the joint sets. The maze joints often have a weathered rind, as shown here. And Jim showed some of these in his presentation as well. That is a lighter colored, look, if you see the ceiling, the lighter colored area, a rind surrounding the joint, and that indicates water movement through the joint. On the fringes of the currently mapped passages, apparently the cave is more joint controlled. But those are the passages that not as many of them have been mapped here. As we've already seen, Helm's Deep Cave hosts many carbonate and sulfate speleothems throughout the maze. Some of the most impressive are the large lectite bushes and the fields of gypsum dust and the long selenite needles. Beyond the visually impressive speleothems, there are numerous crusts, powders, and other crystals formed throughout the cave. The source of the uncommon minerals in the secondary deposits in the cave is thought to be the Murray Shale and the Fork Pane Formation. The Murray Shale is glauconitic. I don't even know what that word means. But it is pyrite rich, and I do know what that means. And it might be a significant source for potassium, sodium, iron, aluminum, magnesium, and sulfur. The Fork Pane may be a source for hydrocarbons. It contains many celestite geodes, and that provides a source of sulfides and strontium and sulfate ions. So there are sources for this stuff. Gypsum is incredibly common throughout all levels of the maze. In many places, gypsum crystals entirely cover the wall, and gypsum dust coats the floors. In other places, selenite needles up to 3 feet long litter the floor, and 2-inch diameter crystals can be found in the mud. Again, Jim showed some great slides of that. The selenite needles range from clear to orange. Large, thick selenite crystals also appear to have an orange needle core, and some needles are banded orange, perpendicular to their length. The banding on a selenite needle might indicate intermittent flooding, which would continuously enrich the walls and mud with sulfate-rich minerals, allowing sustained crystal growth. While black coatings are common, or somewhat common, throughout the cave, the western borehole has large sections of the floor that are covered in a near-reflective layer associated with dripping water from above, often from what the cavers call tartites. And this is a picture of a tartite. They're likely comprised of calcite, manganese, and iron oxides. They grow exclusively in the western borehole, and they are always associated with the black coating below them. Their organic, slimy appearance, combined with the presence of nearby snotites, suggests that these might be partially biogenic. Oops. And this just shows the black floor, as you can see, black coating below one of the tartites at RH8 in the cave. This shows a snotite in the western borehole. I don't think Annette or anybody's been here yet, but obviously needs to be looked at. There are orange coatings throughout the cave. This is one of the galleries showing the coating here. These are probably formed when water seeps down through cracks in the shale, and it's assumed the coating is primarily iron oxide. And as we've already seen, there's also aragonite, anthodite, celestite, and more. Celestite geos, now I see John Hoffeld, we worked on celestite in Hickman County, but I've never seen a geo like this with the celestite. The blue is from the gold, apparently associated with it. Anyway, so celestite is strontium sulfate, and remember there are geodes of it within the Fort Payne, and we're not sure what role this might play in like secondary mineralization that we do see in the cave. The white and yellow crystals observed in the Murray Shale. Now I don't have pictures of these, but there are some small white and yellow crystals, and they were directly on the shale. And they were identified as diadochite and jarosite. But Christian pointed out that when he looked at the microscope, those were the two he could identify, but there were many other minerals in that sample that he simply wasn't sure exactly what they were. In conclusion, three things I guess he really wanted to talk about is the central anticline, the key, hypogene or epigene, how do you like your cave formation, and then diffuse seepage. So the area around the central anticline has been overdeveloped. Oh, one more thing. Fossils. I saw a 3-footer, I thought I was impressed, and then they showed me this photo, and it's like, okay, I give up. The area around the central anticline has been overdeveloped. And that's where you have these massive shale boreholes. It's the highest elevation of carbonate, non-carbonate contact. You have dense faulting and joining. It seems logical that something in the north is going on. High elevation, bigger passages, massive shale. Something's going on in the north. Now, if you take a hypogene approach, a rising waters approach, you can draw a picture of water gathering deep underground along the limbs of the anticline and then traveling upward through the faults and reaching the water table. Once it reached the slow-moving water table, it mixed with the water, making it more aggressive and thus forming caves. This could explain why passage size diminishes as one moves further from the anticline epicenter, and why there is more well-developed passage in the downstream direction north away from the anticline compared to the south of the anticline. But one of the issues with the rising waters theory is that there do not seem to be any large pathways where the water rose through the floor or up through the ceiling. Now these could be obscure. There is the deep sediment on the floors. In the western borehole there are unexplained depressions in some passages. Maybe those are the missing feeders from below. But some, and I think Christian falls into this, might prefer a different interpretation. One of the peculiarities of Helm's Deep is that the cave seems to be homogeneously developed under phreatic conditions across a large area. Taking that by itself, the cave can quickly be compared to, diffuse seepage caves, like Anvil Cave, or what Dr. Palmer would call an Allegheny pattern cave. While not as sharply joint controlled as other examples, like Anvil Cave, this does provide a plausible epigene understanding of the cave. And for now, Christian leans towards that theory, the epigene theory. Diffuse seepage is where he's going. Thank you very, very much. On behalf of